Hi, everybody, and welcome to the second half of Chapter 3. So, Chapter 3, the second half deals with the chain rule. But before we can even go into the chain rule, we have to recall what a compositional function is. So, a composition function has the form f composite g of x, which equals f of g of x. Now, if you remember, when we evaluated a compositional function, we always did the inside function first. And then whatever that result was, we evaluated that with the outside function, which would be the f of x, in this case, just the letter f. Now, an example of that would be something along the lines like evaluate f of g of x if f of x equaled 3x plus 3 and g of x equals 2x. So a long time ago, maybe you learned it this way, maybe you didn't, but the way I'm going to do this is I'm going to write f first with, really big set of parentheses, and I know g of x is going to go on the inside. So since g of x is on the inside, we know that instead of writing g of x, we can just write 2x. And what my goal is to take that result, 2x, and substitute it into the function f. So I would just put the 2x here, and that would give me 6x plus 3. Now we can even take this one step further if you wanted to, and said, well, evaluate using the same functions f of g of 2. So you can go directly into here and just say, okay, well, if we went f of g of 2, well, that's going to equal 6 times 2 plus 3, which is equal to, well, 6 times 2 is 12. 12 plus 3 is 15. The other way to think about this is using, the functional machine or the function calculator, as I like to call it, where what you have is nothing more than just like two computer screens, where the first computer screen or the first calculator is g of x, and the second one is going to be f of x. Now, notice the arrow goes from left to right here. So what I'm going to do is substitute a 2 right here. And the first calculator takes this result, substitutes it right here, and then gives me an answer of 4. But then immediately, it'll take that 4, and I'll put it right in here into this calculator, and it'll say, well, 3 times 4 is 12, and 12 plus 3 is 15. Notice, no matter which way you look at it, you still get the same result. In section 3, what we're going to be talking about is taking derivatives of these functions within a function. And to do that, we need what we call the chain rule. So I already have it written out, so I'm just going to hit Control, or better not Control, I'm just going to click and hit Paste. And right here's our chain rule. So while you're copying it down, I'm just going to go over it real fast. So suppose that we have two functions. We're going to call them f of x and g of x. And they are both differentiable, meaning I could take the derivative of both. So even though it says 1 and 2, they are the same rule. It's just using different notation. So the first notation is going to be the prime notation. The second one is going to be the dy dx notation. So the first says, I'm sorry, I forgot a word here. So if capital F of x equals the compositional function f composite g of x, then the derivative is going to be equal to f prime of g of x times g prime of x. In other words, what you're going to do is you're going to identify what is the outside function and what is the inside function. Okay? Same thing for part 2. Part 2 is just using Leibniz's notation of dy dx. But basically, if you have y equals a function of u and u equals a function of x, then the derivative of y is going to be dy dx equals dy du times du dx. So I think it's just really good. Let's just start off with an example here. So I'm going to say f of x equals the square root of 5x minus 8. Okay? Now, here we have a compositional function, and let me show you why. First, I'm going to rewrite the square root of 5x minus 8 as the quantity of 5x minus 8 raised to the 1/2 power. Now, if you're looking at this, we actually have a compositional function. The outside function is going to be the 1/2 exponent. In other words, you have some stuff on the inside here, okay? But basically, you got something or some stuff raised to the 1/2 power. So that's the outside function. The inside function is going to be the stuff, which is 5x minus 8. So if you think about this, what we're going to do is we're going to take the derivative of the outside function, rewrite the inside function, and then multiply by the derivative of the inside function. What I mean by that is the derivative is going to be the derivative of the outside function. So notice all I did is I took the 1/2, I pulled it out front, and then I subtracted it from 1. And now I'm going to take the derivative of the inside function and multiply it. And the derivative of 5x minus 8 is just 5. Okay? So I can clean this up if I wanted to by writing 5 over 2 times the quantity, 5x minus 8 to the negative 1/2, or 5 over 2 times the square root of 5x minus 8. Now, I know initially this may look a little confusing. So what I'm going to do is go over another example, okay? I think just tons of examples are always good, all right? Let's try something a little easier, all right? We're going to let y equal 3x squared plus 6x plus 7, all raised to the 10th power, okay? Now, in this situation, I'm going to go ahead and I'm going to try to use Leibniz's notation, okay? So our goal, or the directions, would be to find dy dx, or the derivative. So watch what I do here, all right? I'm going to let u equal a function of x. In this case, I'm going to let it equal 3x squared plus 6x plus 7. So in other words, I'm going to let y equal u to the 10th power. And now hopefully you can see that this right here, let me write it in red, this is our y equals some function of u. And then right here, right above, this is going to be u equals some function of x. And we know dy dx is going to equal the derivative of y with respect to u times the derivative of u with respect to x. So what I'm going to do here is I'm going to kind of just do two separate little derivatives, and then I'm just going to multiply them together, and then we can see how this on the right-hand side works out. So the first, let's find dy du. Well, that's going to be the derivative of this function right there that I just circled. So that's going to be 10 times u to the 9th power. Now I'm going to find du dx, which is going to be the derivative of the function right above it, which is u equals 3x squared plus 6x plus 7. So the derivative of that is going to be 6x plus 6. And according to our chain rule, what I'm going to do is take dy du and multiply times du dx. So dy dx is going to equal dy du 10 times u to the 9th multiplied by du dx, which is going to be 6x plus 6. And then lastly, I'm going to substitute in, well, that's a horrible looking b. I'm going to substitute what I let u equal at the very beginning of the problem. So dy dx is going to equal 10 times 3x squared plus 6x plus 7, all raised to the 9th, multiplied by 6x plus 6. So hopefully you can see here how this works. Okay, so this is just our chain rule right here. Now, what I'm going to do here is just do just a bunch of examples. All right. So let's see. The first one, we're going to do find f prime of x for f of x equals sine of 3x squared plus x. Okay? So, if I think about this here, that's my inside function. And then the sine function itself is my outside. So the derivative is going to be the cosine of 3x squared plus x multiplied by the derivative of the inside, which is just 6x plus 1. Okay? So, if you think about it, like I said, there's my derivative of sine. This is the inside. And then the derivative of the inside. And every single problem, every single composition is done the same way. Let's try another one here. F of t equals 2t to the third plus the cosine of t. And this is all raised to the 50th power. So f prime of t is going to equal, well, I'm going to differentiate the outside function first. So pull down to 50 in front, leave the inside the same. 50 minus 1 is 49. But now I'm going to multiply by the derivative of the inside. So the derivative of the inside is going to be 6t minus the sine of t. And I'll just pull this parenthesis in a little bit more. So there's our derivative for the second example. Now let's look at another example. H of x equals e x to the fourth minus 3x to the second plus 9. So from here, we can actually take our e to the x rule and make a more general rule, okay? So in general, the derivative of e to the u is going to equal e to the u times du dx. In other words, when you take the derivative of an exponential function just in general, okay, you rewrite the e to the u and then you take the derivative of the exponent itself. So for our example, h prime of x is going to equal, well, rewrite e to the x to the fourth minus 3x squared plus 9. And then we're going to multiply this by 4x to the third minus 6x. So it's just the derivative of the exponent. And that's it. Let's try another one here. Let's try the derivative of y equals the secant of 1 minus 5x. So if you remember, y prime is going to be, well, let me write it over here. The derivative of secant, in just normally, is going to be secant x tangent x. So in general now, the derivative of the secant of u is going to be secant u tangent u times du dx. So what we have to do here is we're going to write secant of 1 minus 5x times the tangent of 1 minus 5x times the derivative of 1 minus 5x, which is going to be negative 5. Okay? So now that I kind of showed you that, what I want to do is just kind of give you a general idea of all of the trig rules. So, for example, the derivative of sine u is going to equal cosine of u times du dx. In other words, times the derivative of the argument for the transcendental function. Also, if you think about it this way, the derivative of cosine of u is going to equal negative sine of u times du dx. Some specific examples would be something along the lines of y equals the cosine of 3x squared plus 2x plus e to the 2x. Now let's keep it simple. We'll just say e to the x for now. So I just follow the rule directly above. Y prime is going to equal, well, I write negative sine of u. In this case, it's going to be negative sine of 3x squared plus 2x plus e to the x. And then I'm going to multiply this by the derivative of the argument. So it's going to be 6x plus 2 plus e to the x. And please do not get real fancy with distributing and all that stuff. I mean, there's really no need for that. All you really got to do is just keep it simple. That's it. So now I'm going to show you an example where it gets a little bit more complicated, but you have the tools necessary to go ahead and actually find these derivatives. So how about f of x equals the sine of x e to the x. Okay? Now, if you take a step back and you look at this, not only do we have a chain rule, but all the other rules still apply. So on the inside here, we're going to have to use a product rule here. So f prime of x is going to equal cosine of x e to the x times the derivative of x e to the x, which is going to be the derivative of the first times the second plus the second times the derivative of the first. So just to clean this up here a little bit, I'm just going to write cosine of x e to the x times e to the x plus x e to the x. So, all those other rules still apply. The quotient rule, the product rule, power rule, all that stuff all comes along for the ride. Okay? We'll do one more here. So y equals the square root of 2y plus the quantity 3y plus 4y squared all raised to the third power. All right, now this, all you got to do, take your time. Just take your time, all right? So y prime is going to, first thing, let's rewrite this as 2y, or the quantity 2y plus the quantity of 3y plus 4y squared, all raised to the third. And this entire quantity is raised to the 1/2. Now, our derivative is going to equal, let's evaluate the outside function first. So this 1/2 is going to be the outside function. I'm going to pull that down in front. I'm going to rewrite everything inside the parentheses exactly the way it looks. And then I'm going to subtract 1 from 1/2, which is negative 1/2. Now, I need to take the derivative of the inside function. So I'm going to multiply by the derivative of the inside function. So the derivative of 2y is 2 plus, but then I have, and I'm going to highlight this, I have another chain rule inside of this chain rule. So I'll write this one in red. So I'm going to pull the 3 out in front. And then write the inside, which is 3y plus 4y squared, all to the second, times the derivative of the inside of that, which is going to be 3 plus 8y. And I think that's it. So they get messy real quick. Okay, so recap. First, you want to rewrite this as a function of y, which is right here. I'm underlining it right now so you can see it on your screen, raised to the 1/2 power. Then you're going to take the derivative. So you pull the 1/2 out in front. You rewrite the entire inside the way it looks and raise it to the negative 1/2. But then you need to differentiate the inside function. Now, the inside function is another chain rule. So the derivative of 2y is going to be 2. That's right here. And now we need to take the derivative of the quantity 3y plus 4y squared, all raised to the 3rd power. To do that, you take the 3, you pull it out front, and you rewrite the inside. So here's the inside rewritten. And then you're going to take the derivative of the inside, which is 3 plus 8y. Now, with a situation like this, I would not simplify it at all. I mean, you can if you wanted to. It's really not that difficult. But it's a lot. So I would just leave it like this. Okay? So that's going to be it for the chain rule. If you have any questions, please do not hesitate to ask. Okay? This can get very cumbersome very quickly because when you have a chain rule inside of another chain rule, it just expands very fast. So make sure that you are just keeping track of everything. It helps if you can break it down a little bit. Write large, write neat, talk to yourself out loud. But other than that, that's going to be it for this lecture. I will see you in the next lecture when we talk about, I forget what we actually talk about here. Oh, implicit differentiation. So that's going to be just another example of the chain rule all over again. See you in the next one.